It's now a particular pleasure to introduce Luca Rade, who is part of our newly established Junior External Fellows group. This group consists of young and extremely promising researchers. Luca currently is an undergraduate at Princeton University, where he's building a simulation to identify the mechanisms responsible for the evolution of syntropic mutualisms in microbial communities. Last summer, Luca did an internship here at the Complexity Science Hub, where he identified precursors to collapse in stochastic adaptive networks. And we had a very positive experience, and this is also why we thought about how we can include the next generation of thinkers. And so it's a particular pleasure to ask you to take the stage.
So thank you for the opportunity to speak, and thank you to the previous speakers for the insightful remarks. So I want to start by highlighting what I see as the two main approaches in complexity science, both of which are important. Of course, this is not a new distinction, but I think it's useful for thinking about the future of complexity science. So the first is toy models, and the goal here is to understand mathematical processes in the abstract, and toy models can be used to indirectly inspire real models. But toy models are not directly applicable to real systems, and it is important not to claim that they are. I'll get there later. Cellular automata are a classic example of a toy model, and of course there are many other examples. The second approach is developing real models. And here it's important to either start in a domain, the squares at the bottom represent various scientific domains, and then abstract away from that system, making sure to not lose any of the important dynamics. Or if one starts with a theoretical model, to quite quickly move down into real systems and verify that the model is indeed accurately modeling a real phenomena before moving back up. And at some point later in the scientific process, one needs to concretely apply that model again to a real system, either the same one or a different one. And without this second step, one has a toy model, which one cannot claim directly models a real system without this second step. It's very important to emphasize when I say going down to the real system here at the bottom, what I mean specifically is verification by human domain experts. And I think this is a very important distinction with verification through fitting with data. A fit with data is not useful for verifying a model, as you can fit various different models with different dynamics to the same data set. Data is very useful for various other things, but for verification there needs to be a human domain expert in the loop. And particularly a human domain expert who is not a complexity scientist. I'll skip over the example of my own research for time. I think a good example is most of the recent work on critical transitions and resilience of this real model process in action. So again, there's these two distinct approaches, and both are extremely important, but one must be aware when working on a project which approach is being used and adjust methodologies and limit claims appropriately. So I'll come back to this a bit later. Zooming in on the complexity science part, the main point I want to make here is that complexity science is qualitatively different from physics or mathematics. And here I am paraphrasing almost verbatim comments made by Simon Levin and Nigel Goldenfeld at a recent workshop in Princeton, but applying it to complex systems instead of theoretical biology. So the first, second, and fourth bullet point, it's a bit jumbled, make a similar point, that complex systems have unique dynamics, and so we cannot simply tweak existing models from other disciplines. We need to either heavily modify them or develop new models. And so the goal should be building a mechanistic understanding from first principles without taking for granted a priori assumptions which underlie models coming from other disciplines. And then a second major point that came from the workshop is the third bullet point, which is that having just a snapshot of a pattern in time does not give you much information. kind of tying to the data point, various mechanisms could have produced the pattern, one needs at least a bit of temporal data. And lastly, somewhat controversially perhaps, is that power laws are uninformative in general outside of physics, with exceptions of course. I won't go into the details of this due to time constraints, but I think the fact that there's a ubiquitous amount of papers recently on finding power laws, despite the fact that there's no a priori reason to think that they provide huge insights, is a good example of why these principles are important to keep in mind. And one can pause the video or if one wants to read further, here are the full citations. So to pull those threads together into thinking about the long-term future of complexity science, this is kind of summing up the points I've made. The one bullet point I want to particularly emphasize is the fourth one, which is the importance of not overpromising. And I think here it's important to keep in mind the history of catastrophe theory and cybernetics, which similarly were interdisciplinary, and I think they sort of overpromised in the initial stages and then somewhat collapsed as disciplines, despite the genuinely valuable insights that they could bring. And as a young emerging field, there's been a lot of great work already, but compared to how much is still possible, complexity science is still in its early stages. I think it's very important to keep that in mind and focus on fundamental, foundational research right now. So last thing, I just want to mention two potential application areas that I think have been somewhat neglected, or that rather have potential for applications from complexity science. The first is AI safety, which might seem like a surprising suggestion, and there's a very common misconception that AI safety is about preventing a Terminator-like robot that wants to kill us all. But in reality, the academic field is more an engineering problem, which is if we have I should note, smarter than human artificial intelligence, i.e. not today's machine learning algorithms, which compared to human intelligence are fairly primitive, but a more advanced version in the future. How can we ensure that such an advanced agent operates in a complex environment without unexpected responses to inputs that we can't predict? We, of course, can't simulate every possible input in the real world that a advanced algorithm could be exposed to, and so there's a lot of dangers there. And for various technical reasons, it's a surprisingly hard problem. And so I prefer the name advanced algorithmic engineering because AI safety has all sorts of connotations which I think are very unhelpful. And I think partially because of those connotations, it's quite neglected as a research field, despite the fact that this is one of the defining problems of the 21st century. And I've recently been working a little bit in it, and one, it's surprisingly intellectually fascinating, and two, complexity science I think is very important to enter this field. It's currently quite small, somewhat incestuous, and it's dominated by pure mathematicians and theoretical computer scientists. And since the discipline is about agents in a complex environment, I guess that speaks for itself that there is the complex systems perspective is missing. And then finally, I think the general research agenda of evolution, broadly construed, is a powerful unifying research agenda. So evolution I'm construing quite broadly as the change in the dynamics of a system in a particular direction, as opposed to returning to the same state or changing randomly or remaining at equilibrium. I think it's fairly safe to say that it's fundamental to most or all complex systems, and it is integrative across domains and across levels of analysis, and it also helps deal with the problem I mentioned earlier of distinguishing between different mechanisms which might have produced a pattern. It's quite a hard problem, mainly because of the self-referential property, and here I'm quoting Nigel Goldenfeld again, which essentially is a system as it evolves is changing its own equations and dynamics with all sorts of feedback loops, so it's hard to model that and get a grip on it mathematically. And Of course, there's a lot of existing work on evolution in various fields, but there's still a lot to be done, and I think this is a useful unifying theory which would form a good basis going forward for the field. And I would add here that I think that there's interesting synergies here with the information perspective that Peter Sloot talked about earlier, which is another unifying research agenda, and the two, I think, will end up being somewhat complementary in how systems actually evolve and become complex. So this is a quick recap of the major points I've made. Thank you for your attention.